Good evening, ladies and gentlemen. This is video number 332, and in this video I am going to detect arch using arch LM test in Eviews. Let me start with the scheme of the presentation. After introduction, I'll introduce you to the data file that I'll be using, and then I will estimate arch and gauge, and then I will be using various diagnostic tests, but this video will focus on the arch LM test to detect the autoregressive conditional heteroscedasticity. Similarly, I'll also be using other diagnostic tests. I start with the introduction. Autoregressive conditional heteroscedasticity, that is arch models, are specifically designed to model and forecast conditional variances. The variance of the dependent variable is modeled as a function of the past values of the dependent variable, and independent or exogenous variables as well. These are some of the historical references with which the autoregressive conditional heteroscedasticity was developed, and this paper was published by Robert Engel in 1982 in Econometrica in its 50th volume. The second one is Bollerschleff, and this was published in 1986 in Journal of Econometrics. And then we also have Taylor 1986 book, that is Modeling Financial Time Series, which was published by John Wiley and Sons in New York. I'm using this file. This is SP500, and it includes 1305 observations, and this is daily data of the volume from 22nd of May 2017 through 20th of May 2020, and this is the Excel data that I imported in Eviews. So these are the various values from 22nd of May 2017 till 20th of May 2022. So as I mentioned earlier, arch and members of the extended arch family, including Garch, E-Garch, Tarch, and so on, they model time-varying variances of the error term. The simplest arch model is like the following, where yt is equal to alpha hat plus beta hat xt plus et, and variance in the present time is equal to gamma naught plus gamma 1 e2 t minus 1. In this arch 1 model, the variance of this period's error term, that is the variance of the et, depends on the squared residual from the previous period, that is t minus 1. So sigma square t is regressed on e t minus 1 square. So let me share with you the data. Here is the data. This is my data file, and let me open this. Let me open this file. This is SP500. This is the data, and let me check its graph. Here is the graph of the data. This is, so you see there are ups and downs is this data. Let me minimize this, and let me go to quick, and then estimate equation. I'll change this least square to arch, and here I will write my model. So my dependent variable is SP500, and I'll regress this a trend as well as SP500 in its first leg, and I will also use dummy variable for day. So here is my model, and let me change this to 0 because I'm interested only in the simplest arch model, arch 1. And let me change this into variance. So here is my estimated model. This is my estimated model. Let me make it a little bit. This is my estimated model. You see, this is the maximum likelihood arch, and this is the sample adjusted. There are 1259 observation after adjustments, and the lambda parameter value is 0.7, and this is the Garch equation. So if you look at this equation, the coefficient of the Garch is highly significant at t equal to 12.02, and the trend is also significant with t value as 3.7, and this is the lagged value of the dependent variable, and that is also significant. And these are the dummy variables for day. There is no constant in it, so all these dummy are highly significant. This is the mean equation, conditional mean equation, and this is the conditional variance equation. C is equal to 505, and this is significant, and the previous period residual square is 0.95, and this is highly significant. The R squared value is 0.99, the adjusted R square is 0.996, and the Durbin-Watson is 1.57. Let me check some of the. Okay, these are the actual fitted and the residual values table, and let me share with you the graph of these actual, fitted and residual. So these two are the actual and fitted values of SP500, and these are the residuals. After this, I'll show you the residual graph. This is the graph of the residual, and then I'll show you the standardized residual graph. This is standardized residual graph, and let me also show you the conditional variance. These are the values of the conditional variance. There is one spike here right at the first quarter of 2020. Let me also check some residual diagnostics. So first of all, I will check the correllogram with the Q statistics and 36 observation, and if you look at these, all the p values are insignificant up to 5th, and then they are significant at the 7th leg, and so on, and later on. So these are the correllogram, and let me also show you the correllogram square. These are the correllogram square. These are the autocorrelation, partial correlation. These are the coefficients of autocorrelation and coefficient of partial correlation, partial autocorrelation. And after that, I'll show you the normality of the histogram. So the Jar-Cabrera test is here, and p value is less than 0.05, so this doesn't follow normality. And here is the arch LM test, and this test shows that the null hypothesis will be rejected at 5%. And after that, let me go again to the model, and this time I will regress Garch 11, SP500 at trend, SP500 with leg 1, and expand and at day, and yes, this should be. Previously I I wrote here 0. Now I write here 1, and here is the variance again, and here is my new model. This is my new model. See, only the Garch coefficient is not significant, the trend coefficient is significant, and all the lagged value of SP500 is also significant, and all the dummy variables for day are also significant. And this is the variance equation in which the Garch with lag 1 is significant, the previous residual square is also significant, and the constant value is significant, R squared value is 0.99, and so on. And the Durbin-Watson value is 2.27. Let me check some of the diagnostics. Here is the parallelogram of the series, and now all the p values of Q statistics are insignificant, so there is no autocorrelation, and these are the autocorrelation and partial autocorrelation coefficients, so there is no problem with these correlations using Q statistics p values. And now I'll use these are the parallelogram, and again these are also insignificant. Now I'll test for normality of the standardized residuals, and the Jacob-Bera test value is equal to 6 to 1.12, and its p value is 0.00. So these standardized residual doesn't follow normality. And finally I'll check the arch LM test. This is arch LM test, and with one leg, and the test of these results using the F test and chi-square test, both of these values are above 0.05. So we fail to reject the null hypothesis that the model has no arch terms of Q order up to Q order. So we fail to reject. So there is no arch term in this issue in this model. And here are the auxiliary regression. This is the R squared, and the Durbin-Watson is 2.005, and this clearly show no sign of autocorrelation. So ladies and gentlemen, this is how we estimate arch and Garch model, and the arch LM test for testing heteroscedasticity, conditional autoregressive conditional heteroscedasticity. So I hope this was quite helpful for you. If you like this, you may share with your friends, with your colleagues, and if you have any problem, kindly do ask question in the comment section, and I'll get back to you as soon as possible. So thanks for your attention, and if you haven't yet subscribed to the channel, kindly do subscribe, and also don't forget to click on the bell icon so that you can get notification about my other videos. Thanks for watching my video.